Hello, this is the final exam review for Organic 1, fall of 2018. I know there's been a lot of complaints about the fact that you haven't been able to hear my voice. I've been quiet. I've been trying to figure out the best way to do that. Hopefully this will work. Hopefully this reconfiguration will allow you to actually hear my voice. So the final exam is just going to be the topics that were posted, and what we're going to be doing is just going through the previous exam review slides that that correspond to those topics. So I will be posting these slide decks as a larger slide deck, something like that. Figure we should probably go through it because it's been a while. Okay, so first thing, right? So formal charge. So for this, and so what you want to do for the charge, right? It's going to be valence electrons, right? In sort of on the periodic table minus what you have now, electrons now. Okay, so for this oxygen, right? You have, right, for each bond you're going to slice it because each one's worth 2 electrons, so they share it. Right? So this oxygen is going to have single electrons from each one of these bonds plus this lone pair. So on the periodic table, oxygen has 6 valence electrons. Now it only has 5. Right? So that means that the formal charge for this one is going to be +1. If you had multiple formal charges on here, so the overall formal charge would just be that added up. So the overall charge of the molecule. So, yep. Okay, so for resonance structures, okay, so you have to remember that what we're going to be doing is moving around the charge. Okay, and in order for you to have that, you either have to have the atom, in order to be able to participate, either has to have some sort of charge, has a lone pair, or have some sort of pi bond to it. So carbon-carbon double bond, carbon-oxygen double bond, whatever, something like that. So usually the first thing you're going to want to do is draw in the hydrogens. Okay, and so, right, well, here's the carbons. Put those dots in. Okay, so for here where the charge is, I've gone ahead and drawn in the hydrogen as well as these two, although if I gave it to you on the test, it would probably look like that. So you'd have to draw in these 2 hydrogens. But each one of these dots here has 3 bonds shown, so 1, 2, 3. So each one of these has 1 hydrogen available. So then we look and we say, okay, which atoms, in this case, which carbons are going to be available for the formal, or to move that around for the resonance structures? Well, obviously this one because it has a charge. These 2 and these 2 are part of double bonds. Okay, but this carbon here doesn't satisfy any of that criteria. So we're not going to be able to use that one as part of the resonance structure. Okay, so this carbon, right, it has 3 bonds around it. What does it want to have? It wants to have 4 bonds, right? So for that, not 5, but 4. So the easiest way to do is to look at the neighbors. So this carbon here can't participate, so nothing it can do. So we look over here to this carbon, and in this case, what we can do is we can move that bond up there. And when that happens, so this bond here moves up there. This bond we didn't do anything with, so it stays there. Okay, so now this carbon here has its 4 bonds. It's happy. So, and this one maintained its 4, but now it's this one here that has the positive charge because it only has 3 bonds. So that's where the positive charge ends up. Now for here, we're going to look at either side, right? This one we could move this back, but that would just go to that structure. So we keep moving around the ring, and so we look on this side. This carbon can help out by moving these electrons over here. And so when we do that, then we end up, so drawing these hydrogens so you can see. So now this double bond we haven't done anything with, so it's still there. This one has slid over to here, okay, and so now the positive charge is right there. Now normally what would happen is we'd keep going around the ring, but the problem is since this one isn't eligible, we're at the end of the line as far as eligible atoms, and so we stop. So, there we go. So for hybridization, what we're looking for is the number of letters. Okay, is going to be lone pair sets plus bond sets. Okay, and so for this one, for this carbon here, right, we don't have any lone pair sets, right, but we do have 2 bond sets. So this is a set and this is a set, so 2. So that means we need 2 letters. So you start with S and then add P's to how many letters you need. So it's going to be SP. So it'd be SP, and so you can either do this. So that's what it is. It's either SP or SP1. Doesn't matter. Now for this one, for this oxygen, right, we have 2 lone pair sets. And then we have 2 bond sets, a set right here and a set right there. Right? And so for this one we need 4 letters, so it goes SPPP, right? SPPP, right, which is SP3. So there you go. But remember that a single bond counts as a set, a double bond counts as 1 set, a triple bond counts as 1 set. Something like that. So don't forget. Okay, so for this one here, what we're going to be looking for is well, I'll give you 2 structures and a spectrum, and you have to tell me which one it is. So it's not only going to be what's there, but what's not there. Okay. Now you can always assume that the alkane CC and alkane CH peaks were there. So I'm not going to list them because they get because it just confuses students. Okay, so if you look here, and I'm going to give you this chart. So we're looking at 1650. So you come in here to this chart, right? So no. It could be, well, no, it can't be that. It could be the alkene. This is alkene's carbon-carbon bond here. And that's about all it could be. So it looks like. Now this 3050, now it could be the alkene CH. Okay, you come down here and that's about all it can be, stuff like that. And so, the molecule that we're detecting, right, has both the carbon-carbon double bond as well as this CH bond here, right, which would be right there. And so these correspond to here. Now you have to remember, if it's sometimes what you can do is tell me what it's not, because if it was one particular molecule, it would also have to have that. Since it doesn't have this particular, so let's say it had if we had another one that was, say, this, well, we if it was something like this, we would have the carbon-carbon double bond, we'd have the CH bond, but it would also need to have one around 1700, which would have this. We don't have this, so it couldn't be that. So you have to be careful about what it is, what's there and what's not there, and you can knock things out not only for what is there, but what's not. Okay, so for this one, right, we're going to be looking at the functional groups. You have to get 1 point for circling it and a point for naming it correctly. And so we're going to just start at one end. So you come over here and you see this C double bond to O. And remember, for those, you have to look on either side. So we have a carbon on this side and an O carbon on this side. Doesn't matter that this is a benzene. So this is an ester. Okay. Now, alkanes, cycloalkanes, and benzene groups we don't have to worry about. something like that. So here's a benzene, here's a benzene. We don't have to worry about those, something like that. So I'm going to assume you know what those are. Now for here, we have an OH, but there's just a regular carbon next to it. It's not a C double bond O, it's just a regular carbon. Nor is it directly attached to this benzene ring. That would make it a phenol, but it's not. There's a carbon in between. So this one just ends up being an alcohol. Okay, come down here, that's a benzene. So for this one, a nitrogen, right? We've just had regular carbon, carbon, carbon. Doesn't matter. You can have any sort of combination of carbon and oxygen, or carbon and hydrogen. But definitely it's not a carbon-carbon triple bond. That's not there. That would be a nitrile. We don't have that. Nor on these adjacent carbons is there a carbon-oxygen double bond. So since that's not there, that means that this is an amine. Now, amines can have any sort of combination of carbons or hydrogens in here. That's as long as they don't have the C double bond O. So there you go. So for this one, okay. So remember the progression. So you're going to have these ones that we talked about. Which one is the most acidic? So the first thing you have to do is you have to look at find the most acidic H. And 9 times out of 10, it's going to be a hydrogen that's not on a carbon. Okay. Now the this one. So for this one, it's going to be the whatever the sort of, you can see XH. So this is the carbon that, or the atom that has the H attached. The closer X is to iodine, the more acidic. Okay. So for this, so if that's still a tie, okay, then you look for adjacent pi bonds. It doesn't matter if it's carbon-oxygen double bond or carbon-carbon double bonds. If they're immediately adjacent to it, that makes them more acidic. Okay. If that's still going to be a tie, then you look for electronegative atoms. Okay. In the molecule, and this is going to be closer to F. The more acidic, or the more electronegative. Okay, so for this one here, right, the most acidic bond is going to be this pH, and then this one is going to be the NH. Okay, so we've done this. Now this bond here, right, the closer this atom is, either the P or the N is to iodine, the more acidic it is. Phosphorus is farther down on the periodic table than nitrogen. Actually, it's right below it. That means it's closer to iodine, which in this case means that one's the more acidic. Now for this one, okay, the most acidic bond is going to be H is going to be here versus here and here. So these are going to be a tie, right? The OH, right? Because they're both on an oxygen, right? So they both have C double bond O's next to them. Okay, so that's a tie. Now for electronegative atoms, not only do you have this oxygen here, but again, that's a tie. So if this was a carbon-carbon double bond versus a carbon-oxygen, that would oxygen would be more electronegative than carbon, so that would be it. But again, we've got a tie here. So what it really boils down to is fluorine versus chlorine. Now fluorine is more electronegative, right? So with that, and so this is going to make this OH more acidic. Its inductive effects is going to be sucking electrons towards it, which is going to weaken this bond. Okay, so in this case, this is the more acidic of the molecules. But just go through these steps each time, and you'll be fine. Okay. Now you are going to be naming these molecules. I'm not going to go over this in this video. You can go back to the I think it's chapter 4 But that's so the where we go through these. So with that, so you can look at that video. Otherwise, we'll be here forever. So. Okay, so for cis-trans on a cycloalkanes, whether it be 5-member ring or 6, okay, so remember that cis means they're either both going up or both going down, and then for trans you have one up and one down. Okay, so for this one here, the methyl groups, right? So in this case, they're both pointing down away from the ring, right? So this is going to be cis. Okay, and so for here, notice how this is going to be axial down, right? Because carbon-carbon bonds are pointed down, so that means axial is going to be straight down, like that. The hydrogen would be here, that would be the up. For here, the carbon-carbon bonds are pointed up, so that means the axial is straight up, like this, which means you have a hydrogen here that's the down, but it's equatorial. So we're looking at this versus this. This is up, that's down, so this is going to be trans. Now for this, so degree of unsaturation. Okay, I'm going to give you this equation on the equation sheet, so you don't have to memorize it. You just have to know what it means, right? So this is the number of carbons, nitrogens, the total number of halides, and this is hydrogens. Okay, so in this case, right, so the DOU, right, is going to be 2 times the number of carbons, so in this case it's going to be 8, plus 2, plus the number of nitrogens, so in this case 1, minus the number of halides, minus the number of hydrogens. So, excuse me, which is 8. Okay, all of that divided by 2. Okay, so for this one, right, so we 16, 17, 18, 19, so 19 minus 9 divided by 2, so it would be 10, 2, so it's 5. There you go. Okay, so find the chiral. Next one is find the chiral center. Okay, so you can always put in your dots, so you remember. Right, so remember, for a chiral center, you have to have 4 different things hanging off of it. So this one here has only 1 bond shown, so there's 3 hydrogens. This one has 2 bonds, so 2 bonds shown, so there's 2 hydrogens. Here, there's 3 bonds shown, so there's 1 H. Here, there are 2 bonds shown, so HH. Again, this one here, 2 hydrogens. Here, 3 bonds are shown on this carbon, right? So 1, 2, 3. So there's a hydrogen here. And then each one of these only has 1 bond shown, so HHH, HHH. Okay. Now, we can get rid of anything that has multiple hydrogens on it, right? Because that automatically means that it's not chiral, because it doesn't have 4 different things hanging off of it. So that just leaves this group and this group, this carbon and this carbon, to really take a look at, right? And so for here, so what we're going to do is we're going to say, okay, what are the groups, right? So we have a hydrogen, a fluorine, and then we have a CH2 and a CH2. Now that's a tie, right? But that doesn't mean that they're the same. So what we're going to do is we're going to go out one, and it's going to be a CH3 versus CH2, right? And so this one is different than this one. This side is from that side. We have 4 different things hanging off of it, and so we have a chiral center here. Now, what would happen is if you went all the way out and it was still a tie, when you got to the end of the chain or looped back onto yourself, if it's a ring, well then those are they're not different. Okay. Now the other one here, we have a CH2, an H, a CH3, and a CH3. Now what we would normally do is say, like, okay, well that's a tie, so we go out one further, but that's all the farther we can go. So that means these two sides are the same, so that means this is not a chiral center because it has a CH2 and then 2 methyl groups on it. It's no different than having 2 hydrogens on it. So that one can't be a chiral center. It's the it doesn't have 4 things, so that's the only chiral center here. There may be more than one in the molecule. With that, if there aren't any, then it would be achiral. Okay, so for this one, determining R and S. Stuff like that. So you're going to have an arrow pointed here. So this is the carbon you're dealing with. So you're going to be looking at carbon, carbon, hydrogen, carbon. Okay, something like that. And so remember, it's all about weight. So in this case, right, the carbons are going to be the heaviest as opposed to the hydrogens. So this is going to be group number 4. Okay, but since these are all the carbons, we have to look at the bonds. Okay, so for this one has 2 carbon-carbon bonds, right, here and here, and 2 carbon-oxygen, 2 carbon-oxygen, here and here. This one has 2 carbon-carbon and 2 carbon-hydrogen. So that, because 2 bonds are shown, so that means there must be 2 hydrogens here. Same thing with this one. There's 2 bonds shown, so there must be 2 hydrogens. So this one has 2 carbon-carbon, 2 carbon-hydrogen. Now the heaviest bonds are going to be this carbon-oxygen, carbon-carbon, carbon-carbon. This one, the carbon-oxygen is heavier than the carbon-carbon, right? So that's going to make this one number 1. But these 2 are both carbon-carbon, and they're the same amount. So that means that this is a tie, so we have to go out 1. Okay, and so we have 2 bonds shown. So this, so let me do some blue. So this one has 1 carbon-carbon bond right here, 1 carbon-chlorine bond, and 2 carbon-hydrogen bonds. So for this one here, right, 2 bonds are shown, so there must be 2 hydrogens. So for here we have 2 carbon-carbon, 2 carbon-hydrogen. And so for here, the heaviest bond is carbon-chlorine versus carbon-carbon. Chlorine is heavier than carbon, so that means that this is going to be number 2, and this is going to be number 3. Now I usually redraw this to say be like this, so with just the numbers. Okay, so if you're using the hand method, your thumb has to point towards 4. So in this case, it's on a wedge, so it's coming out at you. Your fingertips would start at 1, and then as they curl, going 1, 2, 3 around like that, with that, and so that would mean since you're curling with your left hand, it must be S. Because if you try to do this with your right hand, which would make it an R, if you start here and you try to rotate them back towards the 2 over on this side, you're going to break your fingers. Now for if you're using the steering wheel method, you've got to get 4 behind. Okay, so this is going to be we're going to do this green, red, and blue. So when we do that, okay, so it's like this. When we move the 4 behind, it ends up like this. So rotate. So the 1 is over here, right? The green ended up sliding over here. The 3 ended up over here because that's the blue, and then the red is over here, like that, and then the 4 is behind. Okay, and since we are rotating, so now we've got everything right because we've got to get 4 behind for the steering wheel method. It's going 1, 2, 3 like that. It's going counterclockwise. The steering wheel's going to the left, so it would be, again, it's going to be S. Doesn't matter which way you use it. There's other ways of doing it too, but these are the 2 methods I teach. So. Okay, so for E and Z, right, remember, we're going to be looking at this carbon, the 2 things hanging off of this carbon versus the 2 things that are hanging off of that carbon. So for this one, right, we have chlorine versus nitrogen, right? Chlorine is heavier than nitrogen, so this is the high and this is the low. Now on this side, right, we're going to be looking at that carbon versus that carbon, okay, and they both have 2 bonds shown, so it's 2 hydrogens. Right? So for here, it's 2 carbon-carbon, 2 carbon-hydrogen, right? We have to do that because they're both carbon, so it's a tie. So 2 carbon-carbon, 2 carbon-hydrogen, right? Their heaviest bonds are both carbon-carbon. They both have 2 of them, so it's a tie. So now we're going to go out to here. We're going to compare this one to this one, right? Here, 2 bonds are shown. Here there are 3. Or there's 1, so there's 3 hydrogens. So So for this one, right, this has 2 carbon-carbon bonds, 2 carbon-hydrogen. This one has 1 carbon-carbon, right there, and 3 carbon-hydrogens. So for this case, the heaviest bonds are going to be carbon-carbon, but this one has 2, this one has 1. So that makes this the high side and this the low side. And so you have to look to see where the highs are, right? Are they on the same side? Yes, they are. So it is Z. It is the Z configuration. Next up, we're going to be classifying these. Okay, so first thing we're going to want to do is take a look at the C double bond to O. In this case, right, there's carbons on either side, so that means it's ketone. So that means it's a keto sugar. So it's keto. And then for this one, then we have to count the carbons. So 1, 2, 3, 4, 5, 6, 7. Okay, so it'd be 7. So this would be a ketoheptose. Okay. On this one, right, here's the carbon oxygen double bond here. This is the carbonyl. But notice how it has carbon on one side, hydrogen on the other. So this is an aldehyde. So this must be an aldo sugar. And so for this one, it ends up being 1, 2, 3, 4, 5, 6. So 6 ends up being hexose, so it'd be an aldohexose. Now don't count the hydrogen here, but also don't forget to count that one. But don't count the hydrogen, because we're just talking about the total number of carbons. So there you go. So when we're looking at D and L configurations, for a straight chain, all we're doing is looking at this right here. So the D, for the straight chain, it's going to be pointed to the right, and then for the L, it's going to be pointed to the left. So it's the last chiral carbon, right? So one up from the bottom usually. So like that. So it's going to be here and here. So this one is pointed to the right. So it's D. Here's to the left. Here's to the right. So it doesn't matter about the other ones. Okay. Now for down here for the ring systems. So for the in this case it's the furanose. So with that, what you're looking for is this carbon here. So here and here. It's the carbon sticking out of the ring. Okay, that's not part of the ring. If this is pointed up, then it's D. If this is pointed down, it's L, below the ring. Okay, so here it's below the ring, so that means this is L. Here, this is above the ring, so this is D. So, there you go. Okay, so last one, okay, linkage analysis. And so for here, right, first thing you're probably going to want to do is do your carbons. So and your numbering, so I'll put into dots. Okay, so traditionally, so this is going to be carbon 1, so it's going to go 1, 2, 3, 4, 5, 6. Okay, and so you can either do it that way. The other way you could do it is to know, okay, we've got a 6-membered ring here, so that means that this one out here is going to be number 6. So it's going to be 6, 5, 4, 3, 2, 1. So if you get to this point and it's a 2, that means you've forgotten one. It's most likely going to be either one of these two. You don't count this, the oxygen, because we're just counting carbons. So that's how all of these are going to go. 4, 3, 2, 1, 6, 5, 4, 3, 2, 1, 6, 5, 4, 3, 2, 1. Okay. So now we're going to be looking at these sugars in isolation. Okay, so we're going to look at this one versus just these two. In this case, this doesn't matter. So we look at the bond from here, coming from the left-hand sugar. So this is the left-hand sugar. The bond is right here. It's pointed down, coming out of that left-handed sugar. So that we designate that to be an alpha. And it's going from carbon 1 on the left-hand sugar to carbon 6 on the right-hand sugar. So this is an alpha 1,6. Now for this linkage, we're only concerned about these two sugars. Okay, here's the linkage here. This is the left-hand sugar, so it's going up out of the left-hand sugar, so that makes it a beta. And so for here, it's coming from carbon 1, and then going into carbon 4. Okay, so it's a beta 1,4 linkage. Now this one is the tough one, because again, we're going to look at these in isolation. This one is left compared to this one. Okay, and so this one, right, so that means we're going to be looking at the bond like here and going down. So that makes it an alpha, and we're going from carbon 2 on this side to carbon 6 on that side. So it's an alpha 2,6. So, good luck.